News from the University of Wisconsin. I'm Jack.
Silence.
Chippewa Valley Code Camp.
I'm Reed.
And I'm Aaron.
And today we're going to talk about Stultus, our search engine that we built from the ground up. Okay, so a while ago, I was scrolling Hacker News, as one does, and I found this little post on basically how to build your own search engine with your own code. It gave you the nice little steps, tokenizing, the database, the crawling, all that cool stuff. It was awesome. And I thought, wow, that's a cool idea. I should really do that. So I made a little plan. I thought, okay, make this nice and simple. I'll have a fleet of like small machines in the cloud, little VMs. They'll be scraping, they'll store it in like a SQLite database. Nice, it'll be cool, it'll be small, it'll be awesome, it'll be easy. Next slide, please. And I thought to myself, wow, this seems really easy. How does Google have such a large market share? Is it really that easy? Spoiler alert, no. It is not that easy. It's not even close to that easy. It is not that easy. Sorry. So that little beautiful little plan, nice simple, turned into how we took a simple coding project way too far. So before we talk about the nitty-gritty of how we actually do this and how it works, I'll talk a little explainer on how search engines work so we all have a baseline knowledge. It's pretty simple. You have a crawler that visits a web page, and then it takes all the text from that web page, stores it in an index or a database, so it's reversibly searchable. And then also it takes all the URLs from that page, it has it to the queue, so it can crawl that pages, those pages too. So basically, you crawl to the internet. That data from all those pages are stored in the index, so when a user searches a query, it'll somehow rank the pages in that index, and then best match it to that user's query. Pretty simple. Sounds pretty simple. So again, this is how we started. We thought, okay, a nice 1 CPU, 1 gigabyte RAM cloud VM, not too bad. That's 20 cents a day. SQLite cloud database, not too bad. Put a dashboard in there, search engine on the internet. But there's a couple problems with that. One, if I wanted 30 scrapers, which is a pretty reasonable amount, that's $5 a day. And also, I'm a broke college student. I don't have that money. Two, Kubernetes is an awesome way to orchestrate all your crawlers, all your software. And it's kind of expensive to run the cloud. And again, number 1A, I am a broke college student. Another problem, the internet is really, really big. Google's index, according to an antitrust lawsuit, is roughly 400 billion pages or documents. So 31 CPU scrapers is not going to cut it. So from there, I decided, okay, cool. The cloud isn't going to cut it. That's too expensive. So instead, I bought $400 worth of hardware, old desktops from Wisconsin auction. And the basic plan was to put Kubernetes on those, put a nice in-production Postgres database on one of them, and then tunnel all of it through Cloud Proxy, using the university resources that we have as students. Yeah. And at this point, I was like, okay, that's a lot of work. I don't want to do all that work. So I brought it up to the club, the Student Association for Computing Machinery, or SACM, and I got these guys involved. A couple other people, but they're not here today, so we're not going to talk about that. Just a quick run on how we collaborated. We have a task planner, you'll see that later. Lots of group chats that we didn't need, and no vibe coding. This project was strictly for learning. It was not for building a cool product that would make money. So we used AI a little bit for guiding, questions, that kind of thing, but we did not vibe coding. Also, you'll see this is the graph commits, right? So we started development. This was me working during my winter break, and then we really started development a month ago-ish. No, some commits. All of these 36 commits were last night. Yeah.
It's rough.
So we might be a little tired. We're all running 2 hours of sleep right now. So yeah, please excuse us. Okay. Okay. I'm just going to talk about the crawlers real quick and then hand it over to Silas. So, the crawlers, talk about it a little bit. It's pretty simple. Written in blazing fast Python. It goes out to visit a web page, takes all the text from that, stores it using stuff that Aaron talked about later into a database, and then also takes all the URLs from that page, adds it to a queue in that database for other crawlers to go and get. Actually, go that one. We try to filter out stuff because the internet is unstructured, so there's a bunch of data. Anyone can put any data they want on the web, which means that it's really hard to take all that and put it into a nice structured, searchable, readable data or format. Yeah.
Yeah, so this creates like a ton of data, right? But like, what can we look at for the data? Because creating searches is cool, but we want to really try and learn from it. So we want to track some metrics. So we've created sort of just a simple dashboard to kind of figure out what our project is doing in real time. So we're just sort of searching how many URLs we have, how many unique domains as opposed to like sub URLs of like an existing domain, and how many of our requests are locked, which is quite a few of them, but not too many. We want to be nice with our scraping, so we make sure that we're obeying robust FX and sort of like restrictions on scraping. So we just want to switch on.
All right, the searching. So I was in charge of the searching algorithm for the search engine. This top one is the lady? Okay. Oh yes. Okay. So we implemented our search algorithm similar to how Google does their page ranking, right? The idea is essentially, we take our search output should be dependent on the relevance of a search to the URLs we have stored in the database, as well as the references. So how many times each site is referenced, right? Basically, that ensures that we don't get some extremely niche, unpopular website at the top of our search whenever we search. Yeah. So, diving into the relevance, I came up with a little algorithm here to calculate the relevance, where it depends on prefixes. So whenever you search something, the prefix will be the first third of that word, and then we'll search the websites that we have stored if they have those prefixes as well. And each time they get matched, then the more it's relevant in this part of the algorithm. Bigram score, we'll talk more about that in a second, but basically bigrams are splitting the words up into twos and seeing how many times those show up between the search query and when it's stored in the database, as well as trigram scores, except they're just split up into threes. The word score, so how many times a word is matched from the search query to a URL. And then we normalize this value with respect to word count, right? So that essentially minimizes how important the size of the web page is, because that honestly shouldn't matter too much for whether or not it's relevant or not. Okay, perfect. There's the trigrams here, and it'll check those with all the URLs in the database. Also, the first third of the word is the prefix, and those are our parameters here. There's written out there. This is, we don't have to look at all this, but again, we're looking at the relevance here. So that algorithm that I just showed you, the first part, is this number right here, which we will multiply to the references in a second. I'll explain that. But the important part here is that it's a number between 1 and 2. And so that means that this next part for the references also has to be between 1 and 2, so then one doesn't overpower the other. And if it does, then I can choose by using weights if I want it to. Okay, so the way that we do references is we need some kind of a function that obviously makes a number between 1 and 2. So I tried to come up with a few different things. This is the one that I was using at first. I came up with this, except I didn't like it that much because, as you can see, it scales way too quickly. So that means this right here, reference count, as you can see here, reference count is how many times a page is referenced. So, if I don't know, if BBC has 10 references to GitHub, then GitHub will be more popular, right? And so that's what matters here. However, you can see if it has one reference, then this equation, this old equation, would output 1. But if it had 10 references, it almost maxes out, and it gets exponentially less important for the more references you have. So we need a function that doesn't scale as quickly as this one does. So yesterday, So yesterday I came up with this, where you can see up here, if we have one reference, that gives us a value. One reference gives us a value of 1. 10 references gives us a value of 1.3. 100, 1.5. 1,000, 1.6. 10,000, roughly 1.8. And that, in my opinion, is a really good function for my use case.
I think it should also be noted that he came up with all of this between like 11 p.m. and 2 a.m.
I have all of the photos of the whiteboard. It's fine. So back to this. So we have our relevance now, which I've explained, and we have our reference score. And I also just show the reference count as well, just so it's easy to visualize. So the reference count, we put into that equation, and we get the score of it. And then we multiply the score to the relevance, and we get the total score. Okay, and that means the total score, obviously the biggest total score, will be the number 1, oh, you can barely see it. Okay, will be the number 1 search result. So Disney, when we search Disney, the first result here is DisneyTermsOfUse.com. Second will be Disney Store. Third is the Walt Disney Company. Fourth is Disney ad sales and stuff. It works pretty well, yeah. The database here, these are the tables that we have in the database. So, like I said, we store the words from each site, the bigrams, the trigrams. We store the prefixes of each word, and we store the related URLs. I can't see my thing. And then we store the references, so what each thing references, and then URL token counts. So, oh man, I'm totally wrong. Kill me out. URL token counts.
The number of places per URL.
Yeah.
So the number of files on the tracker.
Yeah. So, and then, we've got bigram URLs, which matches the bigrams to the URLs and all these, and then the total weight. Yeah.
I'd walk through the database. Honestly,
Oh, yeah. We have,
So this is the database.
yes.
This is the database also. Again, this is a Postgres database. So you'll see, thank you, here are all the tables. Got your bigram URL. Oh, so as he said, our tokens are bigrams, trigrams, prefixes, and words. Yeah, so these things, these tables, like URLs, words, bigrams, trigrams, prefixes, those are just lists of that token. And then an ID. Very self-explanatory. As a crawler finds a word that's not in this list, it gets added, it gets a new ID. Cool. And then that ID is matched to our URL in this table. So the ID from a word in there is matched to the ID of a URL. It's a little funky. It looks a little funky. I promise this is a real database. Oh yeah, but here, all the URLs that we scraped. So there's a thing, and then there's the ID, and then the total references. So how total pages that reference that site. I don't know why it looks weird. I think it's just because the links are sometimes really, really long. But whatever, doesn't matter. Okay, so those, the ID from the URLs and the ID from the words or whatever token you have is matched. And URLs. This is going to take a second, they're really big table. Also, so our production database is running on campus, like a full old desktop. It's cool, but we can't access it from here because security and stuff or whatever. So this is running on actually our test database in the cloud, which has 1 gig of RAM and 1 CPU core, and it's storing all this. And it's crawling and scraping, and it's impressive how well it actually handles up to that. That's all Postgres, that is not our stuff. But yeah, so you'll see that this is the ID for the word and the ID for the URL. And you'll see which words are in which ID URLs. Cool. And that's the same thing for all tokens, bigrams, trigrams, prefixes, words. Also logs. I don't even know what's going to be in this actually. These are just all of our logs. Started scraping, finished scraping. Errors are reported here.
Locked.
Yeah, a lot of logs. Interestingly, counterpredictably, so we run all this through a cloud proxy so that UWEC players' IP ranges are marked as bots and don't all get blocked. I guess everybody does that. So a lot of websites will actually just block any IP addresses coming from, we use DigitalOcean, so from any data center like that. So actually we'll show you in a second on the dashboard. But a lot of these are just blocked because we're fortunate with this IP. Yeah, anyway, back to the thing.
So now we get into the hardware, which is kind of my bread and butter here. When it comes to hardware, these are our used desktops sitting in a floor-to-ceiling rack. It's what we could use, what we had on campus. We reached out to our LTS or our IT faculty, and we were like, hey, we've got these desktops, we want to scrape the internet or crawl the internet, and we don't have a place to put them. We want to do this, but we don't have a place to put them. We could put them in our dorms, but we don't want to have an entire dorm dedicated as our data center. So UW-Eau Claire has a supercomputer cluster that they migrated from a building that they're going to be tearing down in the coming years. Unforeseen future, or the foreseeable future. I don't know when it's going to be torn down. But this rack is sitting there empty, so they offered us the space. So we took the space, and we've got everything networked to just 1 gigabit switch. And currently, I mean, your server room has PDUs, but oh my gosh, the PDUs are so nice. I've never dealt with enterprise grade PDUs, and they are amazing. But you can see some fun pictures, of course. So we've got Jack over here. This is when we were moving all of them. So he had these sitting under his bed in his dorm. And so then one of our friends helped us bring them all down to the room, and so then we brought them down and then started working on them in mini cluster and trying to mini cluster them. And you can see that the university actually labels them, so either university or non-university owned. So there's not really much non-university owned things, and so we're pretty well in the numbers. So
It was a surprising but annoying bit of bureaucracy to get through.
yeah.
Big.
But you can see that we label each machine, and each machine will have its own host name associated with it, so it's easy to get to in theory. The UW Eau Claire network makes it a little difficult when it comes to host name resolution, but the networking, it's genuinely the hardest part of this, dealing with a large university's network, because they have so many different things that I can't even comprehend. They have weird things like VLAN here and there, and I think it's VLAN, but maybe it's subnetted. Hard to say. I haven't really asked our main network engineer too much about it, but it's very difficult to make things work because certain machines will be on different subnets and they can't communicate with each other. But hard to say. So it also needs to be secure. And one of the best things about having students is that they like to do stupid things. And one of those stupid things that students like to do, especially technically and capable students, IP scans. And so the university has mitigations, or ways to mitigate that behavior. And so they'll actually cut your internet off temporarily while you're doing an IP scan. Which is a really cool thing that they put in place. But when you're crawling the internet like we are, that's a lot of requests being made. And that it looks very similar to doing an IP scan on a network, because you're making a lot of requests. So it's not exactly conducive for crawling the web. So now we get into the other thing that I worked on, which was clustering with Kubernetes. Kubernetes, if you're not familiar with it, it's an industry standard way to cluster different computers. That's pretty much it. You just deploy pods, but it's hard. It's very hard because it's a very diverse program. You can do so much with it. So finding what version of Kubernetes, if you want K8, K3, etc. Each one has its own very unique use. K3 is more for Internet of Things and lightweight, works great on ARM, but K8 is way more robust. So you have all these things, and it's just so much to take in that I ran out of time. I couldn't do it. So go back. Hold on. And the beauty of Kubernetes is if I were to get it running, which in the future I will, we can just deploy pods. So we'll have our grouping of computers, and we can deploy crawling pods. And so each pod will be crawling the internet, and then we can scale that for how much resources that computer individually has.
A pod is just a Docker container.
Yes. Thank you. And so here we see the K3S server. So we're going to use K3S because it's how lightweight it is. It's really lightweight, and it will be very useful for our needs of crawling the internet. And so in this scenario, we have the server, and it manages basically everything and facilitates connections to the agents. So the agents are the individual computers that then run a kubelet that has container pods. It's pretty awesome, and I got really into it, and so I did like a whole wiki deep dive on it, and then realized at the end of it, I am in deep crap because there's so much to it. There's so much to it. But I digress. So I think I'll hand this off to Jack for future work.
Future work is, I think, the biggest section because, again, we threw this together pretty fast. And we have a lot of ideas. We have like 60 things on the task plan right now.
So for the searching here, some things that I would like to implement, or at least research on implementing, is right now we're computing a lot of our values at runtime, and so maybe pre-computing some of them in the database before we have to access them. So then, for every URL we are scanning for, we don't have to do it at runtime. Also, dwell time scoring. is something that I thought I came up with, which I was very offended when I looked up to see it already exists. I thought to myself, you know, if a user goes onto a website and they leave within a second or a short period of time, they probably went to the wrong website. So you would make it so that website doesn't show up as much for whatever search query they put in, or the opposite, right? If someone spends 5-10 minutes on a website, they probably found the right one, so you would make that show up higher. Also, my research on campus here, or over at UWC across the road, is on, I research RAG and knowledge graphs with the head of the department, and so also exploring a RAG solution to searching, because I know that a lot of search engines now don't use something as static as the algorithm I'm using. They rather use vector spaces or RAG.
Retrieval augmented generation?
Yes. Retrieval augmented generation is what you just said. Yeah.
Also, we'll show you, we'll do a demo. You'll notice that a lot of these URLs we shouldn't really have in the database. Not like they're bad, but like, for example, all these don't have titles in the pages, which means that it's probably not really meant for scraping. Also, there's a lot of parameters in all these pages, like marketing campaign stuff. Parameters you don't need in the database at all. Or like, I don't know what it's called, but like we have a hashtag pound sign, and it leads to like a certain part of the page. I don't even know what it's called, I'm sure you do, but you know. Also a lot of redirect links, we should figure that out. This is the QR code to our task planner. If you're interested, there's a whole section, category just for fun stuff, we called it. That's what we really want to get to, because it's fun.
Oh, wait, go back to the, did you get the QR
Oh, yeah,
code?
I'm sorry.
Yeah, okay.
This was kind of our motto. I saw this one time in a blog post, and that kind of resounded with me. Yeah. Okay, demo time.
So I wanted to mention as well, so for the demo, I waited, I found that usually when I weight word matches higher, I tend to get more accurate results. So right now, you saw the base algorithm for the search, for the search, but I weighted the word matches way higher so that we should get results that match the query.
Yeah. So, this is our front end, beautifully handcrafted by Reed and Aaron. So you can look up cheese. It'll take a second. Again, this database is one CPU. Also, we have not optimized the database much at all. We want to get it. But yeah. So yeah, it's not very good.
We probably haven't scraped anything that has cheese inside of it.
It's a small database.
It is.
So like, there isn't.
They go to the dashboard and you can see exactly how large it is.
Yeah, it's.
Only a few
Hey,
thousand.
no, go back. Go back to the front page. There's a link at the bottom.
Yeah. There you go. Here's a dashboard that Silas was talking about. So this only has 19,000 URLs. And this was just the testing database that we created for like an hour today, I think, some of that. So there's a lot of data in there.
And for comparison, can you recite the statistic that how many does Google scrape per day?
400 billion.
So this is very small data set, and we're trying to like encapsulate the entirety of the internet in 20,000 websites. And some of those, I mean, is that total URLs is every website, so that could be like 100 CNN.
Yeah.
So,
Oh yeah, our production database on campus, we just created that for like 8 hours, and it got to I think 330,000 URLs. So it's possible, but not in my. Yeah. So here's that. What? So search search stuff comes up, it's pretty self-explanatory, you know how this works. And then here's all the scores from the search algorithm from Aaron.
See, so when you search Disney, it does come up.
Yeah, and you'll notice, see, oh, that's awesome. Never mind, disregard.
We scraped a lot of Disney. I don't know why, but
Yeah.
just so happened to.
Yeah. So now, if you would like to try it, we do have a live demo. Yeah, it might explode.
It's a learning experience for all of us, I think.
Yeah, yeah. Search.stultus.rip. There's the QR code. Stultus.rip is our main homepage. This will not be live. We'll take this down at the end of the day. This is not going to remain until we figure out something more permanent.
But once we do figure out something more permanent, it'll be back there.
Yes.
So,
Regular just stultus.rip is like our homepage. More data, more information there. Not really.
Also, on the front page, we'll wait until everyone gets it. Back on the front page, we have a little button in the bottom right corner for all of our profiles and about us.
That one was crafted by you.
Yeah.
I did the main page, so stultus.rip, and then also the search.stultus.rip. And then we got the contributors page, so there you go. But yeah.
Is it working? Is everything good? How's it look?
As long as it at least displays output.
Yeah.
Yeah.
Only search Disney. Only.
Like as long as there are as long as Ginger doesn't show up as like a hey, you have your database is failing.
You meant to write best search algorithm.
Oh, right. One of the things that we wanted to add in the future. Did it work? No, hey!
DuckDuckGo.
Over there, Sandra. Yay!
Last night we tested that and we were the first result.
Yeah, Stultus.
Oh, yeah, actually didn't explain. Stultus. It's Latin for stupid. So I hope that brings some context to the name of the program.
Search engine.
Yeah.
Yeah.
Hey, I'm actually proud of that. That's crazy. Wow.
Isn't that nice?
Yeah, it comes up with Google and DuckDuckGo.
Oh, Firebase, Google.
That's
Technicality. But yeah.
Questions?
Do you have a plan to add a website preview, like the text to this thing?
Yes.
Yeah.
So that's one of the things that we've been working on is like, even last night, the initial concept for this looked way different. We had literally just raw values and URLs. We didn't even have the title. And we're working on getting like an icon like you would see on like Google. You would see like an icon for the, it's pulled from the favicon element of the site. And so we're working on getting that on the left-hand side, and we're going to add a lot more when it comes to that. We're going to also hopefully add toggle ability for like the debug values that you see on the right, so then you can disable that. It's not your jam.
And also, we want to make it so the user can customize the scores, so then you can customize for your outputs, right?
Yeah.
Yeah, one of the like the foundational principles was this is like a DIY search engine, not Google, basically. You have control over exactly how it works. Algorithm is transparent. So if you want to weight bigrams super high, make it really important for some reason, by all means. So we want to have the ability to have the user literally adjust how the algorithm works for them.
And the beauty of open source means that if you don't like it, you can put in a pull request, and we'll review your code, and we might put it in, because we can use all the help that we can get, because I don't think a 12-hour coding session over the course of one night that ends at 5 a.m. isn't really going to come in again, so.
What do you mean? It was great.
Hey, we got this.
Yeah,
before we didn't have a front end, or did we even have a searching algorithm before that?
Well, we had a searching algorithm, but I had to fix it. And also, yeah, the front and back end weren't connected.
Oh, yeah. It was basically all static.
Yeah.
And we're working actually on getting this
We probably-
getting a bit faster because Currently, it waits to serve you the page until it has the search result. So it'll be like buffering, and we would rather have it work with like what we tooled around with last night was the idea of async requests, I believe. So it would be an async request, and it would just send you the template, and then it would shove you the stuff. Because currently this is built with Flask, and so there is some built-in async requests, so you can make like an infinitely loading list. There's examples of that, but it seemed very complicated and out of scope for our coding session last night.
Yeah,
So,
I was gonna say, I think last night we probably got at least a month, works done.
yeah, that graph with the, what was it, like 33 GitHub commits, it's probably gone up to like at least 40 or 45, because we've been working on it today, so.
Also, one of the things we want to do, how most search engines like this work is you send a query and then multiple machines will search different parts of the index. So it's not just one thread going through the entire search engine index. We want to implement that in the future.
Which would make things a lot faster. So, yeah.
Any other questions?
You brought up vibe coding at the beginning, what is that?
That is
Yeah.
telling an AI to code for you, basically. Yeah. Letting the AI take the coding.
And there's tools built into like IDEs like VS Code where you can just install a Gemini extension, and it will literally act as like a agent on your behalf while coding. So it's basically the middleman between you and the actual code. So that's really what vibe coding is, and it's gotten quite the Yeah, I was gonna say bad rap, but some people swear by it, some others don't because it leaks API keys. But
And
I mean,
like Brian Hogan said earlier.
Brian P. Hogan.
Yeah, Brian P. Hogan said earlier. As software engineers, we should not rely on AI. The main idea is that we should understand what's happening, and if you do use it, it should be as a tool. We're still college students. We should be continuing to learn, because what's the point of education if we just go to school and we can't keep everything?
so we got this. Is also not a subdomain, but it's just Dalton Direct, and you can find our GitHub there, as well as I believe that links to our SACM Discord. And then also an opt-out page is also a very thing of note. So if you have a website and you're like, I don't like these guys crawling this, you can reach out to us, and we will respond and say, thank you for submitting a request. We'll remove you from the index.
Again, safe searching.
Yes.
So, do you guys have like meetings or anything that you guys are like looking for more recruits for, or anything like that going into this, or?
I don't think so. This is mainly just a club project. Yeah, we don't really meet specifically for this. We just have club meetings. We'll accept totally pull requests, online discussions, anything. Who wants to help?
Yes.
But yeah, no, we don't have any specific meetings for it.
I mean, we as SACM, all our meetings recently have been on this.
Git, which I think we referenced a few times that night because we had a lot of pull requests and merge conflicts. And so we have had to go through a lot of those kinds of things. So I think that was probably the biggest challenge I saw, at least. I don't know if anyone else has anything else.
I would say just like sort of the the approval processes and sort of working through talking to administrative people and making sure that we're complying with university policies. So all sort of bureaucracy and stuff was kind of a lot. Kind of took it from we want to make just this project randomly to into we kind of have to plan it out a little more. We can't just go into it. We have to think about it first. I think that's.
I think as a group, that was probably the most unexpected thing.
Yeah.
Personally, my biggest issue was the first algorithm I made, it wasn't working how I expected. And just having to retweak and even redo entire parts of the algorithm. The left side I had come up with a while ago, and then the right side, for example, the references side, I just kept as the count, like references count, so how many times a page is referenced, and I just multiply the two together. And then I realized, oh, if references is 100, then it completely outweighs how relevant a web page is. And so that's when I was like, you know what, we have to normalize both of the values to get them between 1 and 2, and then it's going to be better.
So do you have any plans for ongoing testing to make sure that the normalization like continues to hold up and performing that you want it to?
I'm currently building test cases, like a small database for just like a development laptop. So with a small index, I guess you would say. So you can test different tokenizers, different tokens, different algorithms, that kind of thing.
Did you mean specifically for my map?
Yeah, the normalization process. I thought it was really interesting. I'm probably going to steal some parts of that idea because I've been fighting with something else. But how do you make sure that it keeps working the way you want it to, and over time, if things shift, how do you handle that?
Yeah, actually, that's a great question. I really like that question too. Could we pull up this slide again? Yeah. So basically, from a math standpoint, your normalization value has to be your biggest value. And the way you normalize something is you put it in the denominator and you add it to the numerator. And if it's your biggest value, then it will always be a number between 0 and 1. Because then you're adding extra values to the numerator. It'll just always be between 1 and 2. Sorry, not 0. Yeah. No, actually, slide back. Yeah. So, for example, word count is always going to be the biggest thing in this part of the algorithm, because word count is how many words show up. We aren't going to, because of bigrams and trigrams, we don't store duplicates. Word count will be bigger. Prefix score, there's only one prefix per word. And word score is how many times, also there's no duplicates for prefixes. And word score is how many times a word is matched to the search query. And word count, because it also doesn't get rid of duplicates, it will always be the biggest value here. So that's how this side normalizes, is essentially because word count is bigger. Could you go to the next slide? So the way that this one normalizes is, again, we have reference count. This one normalizes a little bit differently. Basically, we're taking, let's just pretend it is a square root. We're making the numerator less than the denominator, and then we're subtracting it from 2. So this number right here will always be between 1 and 0, and then when we subtract it from 2, it'll be between 1 and 2. That's kind of how this one normalizes.
How did you land on 1.2?
I guess a check.
Yeah, that was kind of the part I was wondering about. Like,
Yeah.
will it always be 1.2? Might it change over time?
Yeah, so I tested actually how it looked for example, 2, just regular 2 here. I decided that how I talked about earlier, The rest of them scaled too big or not as quickly as I needed. And so that's why I picked kind of an obscure number here. But as we see over here, my opinion is that these are pretty good values for what I'm trying to achieve. Is, yeah, when it starts small, it will increase and exponentially decrease.
Yes.
Yeah, my question with the bigrams and the trigrams, is that because people misspell things when they're searching? Is that how does that mitigate misspelling, mistyping?
Yeah.
That's what I just want to make sure.
But also permutations of the word.
Yes.
So like
Oh, yeah.
relevant versus relevant.
I agree with spelling.
Yep. Exactly.
Disneyfication.
Any more questions?
Yeah, will the slide deck be published in full anywhere?
We can publish it if you, yeah, for sure.
Like, we'll put it on stolfus.rip.
Yeah.
I'm sorry, I have another question. So I noticed the tables that you showed originally, they were just really two values, like a 1 to 1.
Those were the table names.
Yeah, so do you have deeper tables, like with more values, and how does that impact the performance? Like a larger number of shallower tables versus a smaller number of deeper tables, if that makes sense?
Here it is.
Yeah. So, will it affect performance? It'll affect performance of the scraper, but because whenever you search, if we add something more, I'm not using it in the search, at least yet, then it won't immediately affect the time of the search. Yeah. So, does that answer your question, or was there more to it?
So, I guess I'm wondering, is it typically faster or better within a database when you're trying to optimize performance and make it perform as quickly as possible to have a larger number of tables that have like less information within them as far as like columns? Or is it typically better to have fewer tables that have more columns? I mean, how does that interact with performance and other things that one is thinking about with that?
With that, we might have to do some join statements, which would require extra compute. I think the join statements would possibly hinder the performance. I'm hesitant to say that, seeing as I am a freshman and CS student in like a group of upperclassmen. So, but I'm taking database systems right now, so learning about SQL.
So, from my understanding, it's good to have smaller databases where you can have an index that points to a different database, and then when you join them together, actually joining them is pretty fast, and that part should be pretty efficient, from my understanding.
But also, I think the bigger thing is, not right now, but eventually when you cluster your database, so you do different parts of the query on different threads, different machines. I'm not sure which one would be more fast with that, but I think whatever was faster with that is probably the most important, in my understanding.
We could split the selection and stuff.
We are not experts in SQL.
Yeah, if you can't tell.
I can also see how it would also be, just from a maintenance perspective, having everything broken out in such a way. This is a lot easier to, like, just see what you need to see rather than wading through scads of columns and trying to remember where everything is. So, I mean, from a user maintenance perspective, I think it makes a lot of sense. It's just something that I'm always fighting about. Do I dump a bunch of data into one table or have 1,000 different little tables? And I don't have anybody that I can answer.
Yeah, we'll definitely be looking into that, because that's something that I hadn't considered, especially with clustering and splitting up the searching. I think that is something that we really should look into. So,
Last night we had our production index, and then Aaron made some changes, so we had to just restart and start over. And I still had to drop all the tables, and there was like 300,000 URLs or something, and it took an hour to drop all the tables, and that was just kind of funny.
That's something about the performance of small versus big. We run 3 Postgres services for the entire North American continent, I mean, just billions of alerts per day for file events and click handlers. You can always just do both. Postgres has a thing called reuse. You can pre-compute any joined query or calculated query from max whatever. If you can define it in SQL, you can define a view for it, and you can pre-compute it. It will slightly increase your insert times. But then you have a table that's already flat, so you can have your cake and eat it too. You can have a fully normalized and a fully denormalized table. And then you can just make as many as you want. At the end of the day, space is cheap, RAM is not.
that is really good. I like that. Good to know, thank you.
Yes, kind of going off that, it's just like kind of balancing whether something is queried enough, like a similar enough way that you can, that's better to store it rather than each. It's a balancing act.
That was something we figured out last night too. Pre-computation versus